Next up, let's look at some trigonometric functions of what are called special angles. Now, these angles that we're going to work in this segment will be actually carried across to looking at those being the angles in the first quadrant of our trig angles in standard position, and then using a lot of symmetry and the properties that we learned earlier in the segment of the trig angles in standard position, we will actually extend off of the ones we're going to learn in this video to trig functions of nice, quote-unquote, nice angles throughout the entire rotation of the circle. But for here, we're just looking at it in terms of if it were in a right triangle. Now let's recall what our trig ratios in our right triangle trig are defined to be. So remember that if we're looking at the sine of an angle theta, well, the sine of a theta in a right triangle is the ratio of the opposite side divided by the hypotenuse. The cosine of an angle theta in a right triangle is the adjacent side divided by the hypotenuse. The tangent of an angle theta in a right triangle is the opposite side divided by the adjacent side. And then our other three trig functions are reciprocals of these. So the cosecant of theta is hypotenuse over the opposite. Secant of theta is the hypotenuse divided by the adjacent side. And the cotangent of theta is the adjacent side divided by the opposite side. Now recall that when we're looking at this, we have our right triangle. So the theta we're talking about in all of these definitions when we set it up is one of the acute angles in that right triangle. And whichever angle you call the theta, the one you're focusing on, your hypotenuse is always opposite the right angle. So it's always the longest side of the right triangle. But the adjacent side and the opposite side are relative to which of the acute angles you're talking about. So when you have your angle marked, you want to think the adjacent side is the other side that helps make that angle. And the opposite side is the one that's across from it, not touching or not being one of the rays that make the angle. So this would be an example of setting it up with the naming of your hypotenuse, your adjacent, and your opposite sides. We looked at finding these ratios of just any angle in a previous video, and in this one we're specifically going to talk about special angles, and the special angles we're going to talk about are the ones that come from the right triangles that you worked with in geometry. Specifically the 45-45 right triangle and the 30-60 right triangle. So let's remember that if we have a 45-45 right triangle, it's a right triangle and both of the angles are 45 degrees. We know that the total measure of the angles in a triangle have to equal 180 degrees. If it's a right triangle, one of the angles already is 90 of that 180 degrees. And with the extra 90 that's left from 180 minus this 90 for the right angle, if I divide that exactly in two, I will get 45 degrees for each of those two angles. So when that happens, we actually have another property in geometry that says if you have base angles in a triangle congruent, then sides opposite those angles are congruent. So when I have a 45-45 right triangle, the two sides, the legs of the right triangle are the same value as each other. I also know from right triangles in general that from the Pythagorean Pythagorean theorem, leg squared plus leg squared is equal to the square of the hypotenuse. So if we look at this whole setup, and normally we would say that our leg side is A and the other leg side is B and the hypotenuse is C, I know that A squared plus B squared is equal to C squared just because it's a right triangle. But since it is a 45 degree right triangle, I also know that A is the same as B. The sides are congruent. So that gives me A squared plus A squared is equal to C squared in a 45 right triangle. And I have like terms, so I can combine them. That gives me 2A squared is equal to C squared. And if I wanted an expression on this triangle that's specifically set because it's a 45 right triangle, let's go ahead and solve this for C by taking the square root of both sides. So the square root of both sides would give me the square root of 2A squared is equal to the square root of C squared. All the sides are positive, so I don't have to worry about the plus or minus. Well, square root of 2 is not anything that simplifies out of the radical, but it's multiplied to A squared, so I can take the radical separately. So it's the square root of 2, and then the square root of A squared is A. So this is A times the square root of 2 is equal to C. So in any 45 right triangle, both of the legs are going to be the same measure, and I can get the hypotenuse by taking the leg times the square root of 2. That's true specifically in a 45 right triangle. You can't do it if there's different measures on those acute angles, but it's true for those. So what that does for me is it lets me find all of the trig ratios of a 45 degree angle using this property with this right triangle, this special right triangle. And because of the property of similar triangles, even if I had a triangle that had like 4, 4, and 4 times the square root of 2, and I set up all my ratios and I then simplified removing common factors and then rationalized the denominator, or if I had 8, 8, and 8 times the square root of 2, simplified removing common factor pairs in the numerator and denominator and rationalizing the denominator, I always get the same simplified ratio for the trig function's 45 degree angle. Well, the sine of, now I'm not going to write it as theta, I know its angle measurement is 45 degrees. The sine of 45 degrees, we have to pick one of them. So I'll just go ahead and pick this one as the one that I'm focusing on. So the sine of 45 degrees, well, the sine of an angle is opposite over hypotenuse. So that's A over A times the square root of 2. Remember, we are going to remove common factor pairs between the numerator and denominator and rationalize the denominator. I have a common factor pair of A's. So right now that's 1 over the square root of 2. And then when I build this by multiplying top and bottom by the square root of 2 to rationalize it, I get the sine of 45 degrees is the square root of 2 over square root of 2 times square root of 2 is square root of 4, which is 2. So independent of the triangle, if they ask me for the sine of 45 degrees, it's equal to the square root of 2 over 2. How about the cosine of 45 degrees? Well, because it's a 45 right triangle, even though I'm doing this angle for my 45 degrees and cosine is adjacent over hypotenuse, since it's 45 right triangle, the opposite side and the adjacent side have the same numerical value. So I'm still going to get a over the square root of a times the square root of 2. I'm still going to have the a's cancel. I'm still going to rationalize and get that that's equal to the square root of 2 over 2. So when you have a 45-degree angle, the cosine of your 45-degree angle and the sine of your 45-degree angle are each the square root of 2 over 2 ratio. How about the tangent of 45 degrees? Well, for the tangent of 45 degrees, it's opposite over adjacent. So that's just going to be a divided by a, but a non-zero number divided by itself is just 1. Now let's look at the other 3 trig functions of 45 degrees. So the cosecant of 45 degrees, well, that cosecant is hypotenuse over opposite. So for this 45-degree angle that we're looking at, it's the hypotenuse, a times the square root of 2, over the opposite a. So when I have a times the square root of 2 divided by a, my common factor of a's will cancel, and my square root of 2 is in the numerator, so I don't have to rationalize it. I just get the square root of 2. The secant of 45 degrees, the exact same thing's going to happen, and I'm going to get the square root of 2. And then for the cotangent of 45 degrees, that is your adjacent over your opposite, but that will just give me 1. So these values, the sine of 45 degrees being the square root of 2 over 2, the cosine of 45 degrees being the square root of 2 over 2, the tangent of 45 degrees equaling 1, the cosecant of 45 degrees equaling the square root of 2, the secant of 45 degrees equaling the square root of 2, and the cotangent of 45 degrees equaling 1, those are trig functions of 45 degrees equal ratios that you should memorize. They're going to be used over and over and over throughout your work with trig, so you want to make sure that you get them in your mind, that you have them right in the forefront of your memory when you need to use them. That being said, if you ever forget what it is, just try to remember where it came from. Make yourself a 45-45 right triangle. If you don't want a, and a times the square root of 2, put like 3 and 3 or something and use the Pythagorean theorem to get the remaining side. But you can always recreate these values from making yourself a 45-45 right triangle if for some reason you just blank out and you don't remember what those values are. Okay, next up we're going to look at the 30-60 right triangle. With a 30-60 right triangle, you want to start with actually an equilateral triangle and remember some properties with that, and then use the Pythagorean theorem. So we're going to start just with an equilateral right triangle. Equilateral meaning that all 3 sides are the same. So I'm going to just put S for the lengths of the sides. Now, if all 3 sides are the same length, then all 3 angles have the same measure. Remember, there's 180 degrees in a total of the interior angles of a triangle. So if I divide that equally by 3, I get 60 degrees for each of the angles. Now, this isn't a right triangle, and I want to get ultimately to a 30-60 right triangle. So what we're going to do here is we're going to drop an altitude down from the vertex angle to the opposite side, so it meets that opposite side perpendicularly. And if you have an equilateral triangle like this and you drop that altitude down to be perpendicular to the base, then it actually has a property that it bisects the opposite side. So basically, actually, since these 2 sides are congruent, when I drop the altitude down, I cut the opposite side. So if I cut S in half from that altitude over to the other vertex, that's 1/2 times S. And it also bisects the vertex angle. So 1/2 of 60 degrees is 30 degrees. Now what I'm going to do is I'm going to take and erase half of this equilateral triangle just to show the right triangle. So now we have our half of our equilateral triangle, and we have a right angle from the altitude. We have half of S for this leg of the right triangle, and opposite the right angle is the hypotenuse, so S is the hypotenuse. So here again are relationships that you learned in geometry. When you have a 30-60 right triangle, again 180 degrees total, 180 subtract the 90 for the right angle leaves you 90 more. So if one of the angles is 30, 90 minus 30 is 60. If one of the angles is 60, 90 minus 60 is 30. So that's how you get that 30-60 part. And notice that the side opposite the 30-degree angle is going to be always half the hypotenuse, because it is that part that we had remaining when we brought the altitude down and bisected the angle and bisected the side. So whatever this hypotenuse is in a 30-60 right triangle, the side opposite the 30 degrees is always going to be 1/2 of what the hypotenuse was. So that's a relationship that we have. Now the remaining leg of the right triangle is this altitude that we dropped down. And I can use the Pythagorean theorem to get what that is. And I want to know what that is. We'll just call that A. So a squared plus 1/2 of S squared is equal to S squared. That gives me A squared plus, this is 1/2 times S quantity squared. And when you have a multiplication in a parentheses with a square on it, each factor gets squared. So 1/2 times 1/2 is 1/4. And S times S is S squared. Now I want to solve for A because that's the part that we don't know yet. So we are going to subtract 1/4 S squared from both sides. So I get A squared is equal to, well, 1S squared subtract 1/4 S squared leaves me with 3/4 S squared. Take the square root of both sides, and remember I don't have to remember the plus or minus because that's the sides of lengths of a triangle, so they are positive. So A is equal to, and then think about what you can do for your radicals. You can't break radicals up over addition or subtractions, but the property is if you have all of the quantities being real, the square root of a product is the product of the square roots, and a square root of a quotient is the quotient of the square roots. So I can think of this as actually S squared over 1. I can think of that as 3S squared divided by 4. So then I would have an S over 2 times the square root of 3 that would come out of that. So square root of S squared brings an S out, and it's in the numerator. Square root of 4 brings a 2 out, and that's in the denominator. And the square root of 3 doesn't come out, so it's still in the process. So our A here is S over 2 times the square root of 3. Now you may recall from geometry that if you had the hypotenuse of a 30-60 right triangle, then the side opposite the 30-degree angle is 1/2 the hypotenuse, and then that has the 2 already and it has the S already. So then the side opposite the 60-degree angle is the square root of 3 times that shorter side. And that's kind of how you were to work with those. For our purposes, we want to use this to find our trig ratios. And again, with all the common factor pairs that we remove and the rationalizing that we do, if I have similar triangles that still have the angles 30, 60, 90, but maybe have other lengths of the sides in like proportion, similar triangles, their angles, corresponding angles are congruent and their sides are in proportion. Well, those sides in proportion part of it means the common factor pairs will remove. and I'll have a set number of simplified ratios for each of my trig functions of these angles. So let's start with the 30-degree angle. Sine of 30 degrees, so this is the angle we're focusing on. So since 30 degrees is the angle we're focusing on, s over 2 times the square root of 3 is the adjacent side. 1/2 s is the opposite side, and s is the hypotenuse. So the sine of an angle is the opposite over the hypotenuse. And when I take 1/2 s, divide by s, common factor pairs of s remove, and I just get 1/2. The cosine of 30 degrees is the adjacent over the hypotenuse. So when I take s times the square root of 3 over 2 and divide that by s, and you can think of that as dividing it by s over 1, when you flip and multiply, the s's will remove as a common factor pair, and you'll just get the square root of 3 over 2. For the tangent of 30 degrees, it's the opposite over the adjacent. So when I have my s and that 1/2 s, I'm going to write that as s over 2. So s over 2 divided by s over 2 times the square root of 3. My s over 2's will remove as a common factor pair, so I'll get 1 over the square root of 3. But then we multiply top and bottom by the square root of 3 to get that rationalized to be the square root of 3 over 3. For our cosecant of 30 degrees, it's the reciprocal of sine of 30 degrees. So it's 2. The secant of 30 degrees is the reciprocal of cosine of 30 degrees. So then when I flip it and rationalize it, I'll get 2 times the square root of 3 over 3. Then cotangent of 30 degrees is the reciprocal of tangent of 30 degrees. So reciprocal it before you rationalized it. Before we rationalized it, it was 1 over the square root of 3. So when we take the reciprocal, that's just the square root of 3. And I forgot my degree mark, so make sure that you have that. Some things just to talk about to make sure that you do is good notation. Trig functions without an angle associated with them means nothing. In fact, think about it this way. If your teacher were to just say find and they wrote tan and they didn't put an angle after that, is that a question you could answer? No, you need to know what angle the tangent is acting on to what it is that you're supposed to give as an answer. So you can't have it without an angle after it. It has to have the tangent of either a name of an angle like theta or a measure of an angle, in which case we can then look at the ratio. But you have to have your trig function acting on an angle is equal to the trig ratio. So you need to make sure you have that. Also, your angle measurements, if they're in degrees, you have to put the degree symbol on it. If they're in radians, you don't put the degree symbol on it. So just be careful about that. Okay, we still need to do the trig functions, the 6 trig functions of the 60-degree angle. So that's what we're going to do next. I'm going to take just a minute to get this out of the way, and then we will find those trig ratios. 60-degree angle, s is still the hypotenuse, but now this 1/2 s is the adjacent side, and the s over 2 times the square root of 3 is the opposite side. So sine of 60 degrees is equal to, well, sine is opposite over hypotenuse. So it's going to be s over 2 times the square root of 3 divided by s, and think of that as over 1. Flip and simplify, you get the square root of 3 over 2. The cosine of 60 degrees is the adjacent over the hypotenuse. So 1/2 s divided by s. The common factor of s's remove, and I get 1/2. the tangent of 60 degrees is the opposite over the adjacent. And so I have s over 2 times the square root of 3 divided by s over 2. And I just get the square root of 3. The cosecant of 60 degrees is the reciprocal of the sine of 60 degrees, or I can think of it as the hypotenuse over the opposite. And I will see that that is 2 times the square root of 3 over 3. The secant of 60 degrees is the reciprocal of the cosine of 60 degrees, or I can think of it as hypotenuse over adjacent, and that gives me 2. And then the cotangent of 60 degrees is the reciprocal of tangent of 60 degrees, or I can think of it as the adjacent over the opposite and simplify, and I get the square root of 3 over 3. So again, just like I mentioned with the trig functions of the 45-degree angles, you're going to want to work with knowing the trig functions of the 30-degree angle and the 60-degree angle. Now, it looks like it's a ton to memorize, but again, if you ever forget what it is, just make sure you remember where it came from, and you can recreate it really easy just by knowing the basic trig ratios from your right triangle trig. And also, there's a lot of connections going on in here that help you. Once you just tag part of it, you could just get the rest of it from the relations that are connecting everything. Notice that the sine of 30 degrees is a half, and the cosine of 60 degrees is a half. 30 degrees and 60 degrees are complementary angles. They add up to 90 degrees. In a right triangle, they're just these other two acute angles, but you've switched reference of which one you were looking at, so the opposite and the adjacent sides by referencing have kind of been swapped. So when you have complementary angles, the sine of an angle is equal to the cosine of that angle's complement. And that's why it's called cosine of the complement of it. The cosine of an angle is the same as the sine of that angle's complement. So you see how that happens across the board. And that also happens then with tangent and cotangent. So the tangent of a 30-degree angle is the same as the cotangent of a 60-degree angle, because 60 degrees is the complement of 30 degrees. And also happens with secant and cosecant. So that cofunction idea is that relationship between the trig function of an angle and its cofunctions ratio of the complement of the angle. And then also what we're going to look at then soon is, in another video, it will be looking at finding these trig functions of the nice angles, but in their radian measure instead of in their degree measure.